Thanks, Sarah. It's great to see everybody here tonight for the Scottish Data Science and Technology Meetup group. We're delighted to have Colin who's going to be talking about visually driven data science and analytics in Formula One and beyond. I'm Chris, as Sarah mentioned. I lead the data science team at MBN. So yeah, Colin's going to do usual format, his presentation. We're going to have Q&A at the end. Kat will run round with a mic. Big thanks again to the guys at Product Forge who are bringing the live stream for us tonight. So to make sure that everybody online can hear the questions, make sure we'll pass the mic to you when you've got one. Any further ado, on you go, Colin.
Thank you. Okay, so I'm going to talk about the work we do and I've been involved with Mercedes Formula One team, and then actually talk a little bit about visually driven data science as well. That's something that I've done for a long time, and I think that really changes how you work with data science in general. So I'm going to do a mixture of some slides, a mixture of some live demos on a browser, and then I'm going to do a mixture of an actual live data science tool where we'll build and analyse models all there and then using Python and visual analytics. So that could really probably will go absolutely wrong. So I want to prep you. This is the first time I've had to talk in person in 2.5 years, and it dawned on me this morning, and I tried to practice my talk, and I realised it's far too long, I'm doing far too many things, and I thought, oh, but it's in person, and now I'm terrified. So, and it reminded me, I got asked to give a talk years and years ago. It was the first time I talk abroad in Barcelona. I was like, wow, talking in Barcelona, that's cool. And I was sharing my screen, it was a big auditorium, and I thought I was showing them my analytics tool and taking them through it, but actually all they could see was my dog. And I was like, oh no, what have I done? But what I like was when I see, this is my dog Poppy, and this is a big field just outside Stirling. And I suddenly thought she's an interesting example of data science in some ways, because that field is huge. And I opened it, and when she started going in that field, she had no ball. And she bolted into the middle. I have no idea how, like it's a few acres, and somehow she found that ball. And I think we aspire like for AI to match human intelligence, but I think we should aspire for AI to match Poppy's intelligence, because that is a great example of anomaly detection. So, you'll probably see it a few times as I try and screen flip, but let's jump back to the slides. So I want to take you through a little bit about, just disclaimer as usual, a bit about TIBCO. I imagine many people might not have heard of TIBCO, but TIBCO are a big IT company who really produce lots of software. They do it in lots of areas. They've been around for decades. They work with like all the biggest stock exchange, banks, airlines, every industry we're in, as well as motorsport and other things like that. They've got a connect area, which is like APIs and connected data, unify, like data virtualization. But the interesting bit for me is obviously predict. So that's really data analytics and data science. And we do it at data at rest. We do it in real time as well. So that's what I'm going to demo and take you through today after the Mercedes story. So for those of you who don't know, obviously Mercedes are a massively successful team. We partnered with them in 2017, so we've been with them quite a few seasons. They've got 2 technology centres, Brackley and Brixworth, and clearly I'm standing in front of the screen for the stream. Subtly, yeah. Nope, not at all. And so we started that relationship, and they're a hugely successful team. They've really dominated the hybrid era, that started when they brought in this sort of mixture of combustion engines with battery-powered, electric-powered cars. This is a nice picture. I quite like the idea here, is because this was with Mercedes, I think, in the 50s, where Fangio was dominating the racing then, and then the new cars as they are this season. And I think the new cars are really cool this year. They just look futuristic, they look amazing. But when you think about the transition there, and I think this applies to data science, what this car is actually at its core, it's the same as this car in many, many ways. In there, you've got a combustion engine, and you've got some air intakes coming in to cool the engine. You've even got a curved body, clearly thinking about aerodynamics even in the 50s. But here, we've got much the same. You've got air intakes, you've got a combustion engine. Okay, there's batteries and stuff powering it, and you've got all the aerodynamics as well. And data science is a little bit like that. We call it data science now, but really over decades, we've been doing the same sort of modeling analytics. It's just we've got more powerful at it. We've got better algorithms and we've improved. But at its core, it's about using data in the best way, understanding and constantly evolving. So there are innovations, but for me, over the last 20 years or so, I've been doing analytics and data science. It's really about the evolution of constantly improving and learning. So there's a bit of text on this slide, but the main thing I'd say is really emphasising the data that comes off the car. So in Formula One, they're dealing with obviously data as it's coming off the car in real time when they're racing. And actually, they don't take all the data live. When the car comes into pits, they even download extra data because there's so much. They can't take it all in. And sensors weigh a lot. So actually, the more sensors you put in cars to registering, that's extra weight. And you think about how sensitive an F1 car is. But they've got 50,000 data points, more than 400 gig per car, for each race to sift through. And then they've got all their data at rest. And one of the kind of amazing things about Formula One and having been down and worked with the team, the speed they have to work at. They fly out on a Wednesday to a race. They've got to prep, they've got to get the car ready, they've got to constantly assess it. And then they come home maybe Sunday, Monday, and then the next week they're at a different track. Totally different set of circumstances, weather, profile of the track. And they're constantly reacting. So they've got to do analytics and data science at a sort of extreme that I think many industries don't experience. So this is a couple of pictures I took when I was at Brackley, the garage, a couple of years ago. Sadly, that was the last time I was there because of the pandemic, which really stopped the travel, which was such a shame. But you can see they've even got, if you ever get offered the tour of the Mercedes garage, definitely take up, it's really fascinating. The technology they have, from 3D printing of plastic parts to metal parts to the wind tunnel, to even the fact that you can sit and see the real car. That was a car that was raced, it's just in the reception, which is quite spectacular to sit and look at. So they've got a great setup there. But this quote from Mike Sansoni, who I worked with, he talks about uncertainty and unknowns. So he's looking at that 0.1% of uncertainty, because they need to know every tiny detail and when it can happen and predict that and react to that instantly. And that is absolutely key to their success. So they use lots of simulations and lots of analytics to achieve that. And then when I was prepping for this talk, Valtteri was really nice to me, and he published a few quotes. And he actually put this out a couple of weeks ago. And basically he said the computer says no, and that's what he experienced at Mercedes. And if you read the quote there, he's basically saying it's how the top team works, that actually they would override the driver's input sometimes about car setup, because they had so many good simulations that he could analyse and filter and check there and then. And the interesting part is what he says, Lewis felt the same. He wanted to go in a direction, but the engineers would say, no, this is what the computer and the data analytics show. So it shows how powerful and how seriously they take analytics and simulations and data science at the team. And to be the top team, or certainly the top team of recent times, that shows you how useful it is to be in this industry in general. What was interesting is the last point where he says, the pretty advanced technology and simulation tools, and it allows it to be like complete. Quite often the computer was right, but not 100%. And that's quite a nice admission that actually the data did work. So for a Formula One driver who obviously has so much input and so sensitive to feel the car, to acknowledge that these simulations also were very often right, again, just shows the power of analytics. So I'm going to take you through a few of the examples that we've done. We've got a lot of YouTube content with the team, the Mercedes team, that you can look up and watch as well. But I'll take you through some of the key projects we've done with Mercedes. Obviously, I'd love to show you all these things, but if you know F1, you know how secretive it is and how sensitive. So I can't show you the real information, but I can give you a nice summary of the types of things we've done. One of the key things was a cost visualizer tool, and I'll show you a short video that actually shows the tool itself as well. If you follow F1, a budget cap came in a couple of years ago. And for the first time ever, these teams like Mercedes had to account for all costs. That's cost of the car, research, staff, etc. So anything that went into development of the car. And that was a huge change, because before it was a free-for-all in terms of budget. So they had to react really fast. And so this video here, if it plays, I'll just let you see. This is by Oscar at Mercedes. And, oh, I knew that would happen. I absolutely knew I'd accidentally click off it. But he actually shows the dashboard that they use and developed, and it's an incredibly hierarchical nature. So if we just pause the video there and just go back to that screen, this screen you can see here is this sort of hierarchy. I wish YouTube would stop trying to show me adverts. It's showing you a hierarchy of the cost of the car. You probably can't read it, but it's starting with the car, and then it breaks down into the components of the car, like, you know, the chassis, the wheels, and then you've got 4 wheels, and they've got different suspension parts, they've got different bolts, they've got different alloys in them. So they got this down in this huge hierarchical structure, and then they needed a tool to actually analyse that and account for that. And then they could see where the costs were. If we break the car, if somebody crashes the car, if something breaks down, how much cost is it? Where can we trim costs and save money to put more money elsewhere? So they used this dashboard, and this is using TIBCO Spotfire analytics tool. And we used some nice sort of visuals here that are developed using JavaScript visuals to sort of make that interactive to go through the visual parts. The other things that are really important to the team are things like wind tunnel. So the teams only get a set amount of wind tunnel research and time they're allowed to do. So they could print parts or test a new part for the car, but you can't put everything through it. And that's again to help balance the field so that smaller teams who maybe can't afford or don't have the time to do huge wind tunnel runs, you know, it balances it out. So we helped Mercedes there again with building a model that could predict the likelihood of success of a part. So if you take into different inputs, and then you could say, well, we've got 30 parts we want to put through the wind tunnel. Which are highest probability of success? You know, we can only afford to do 10. So again, analytics, simulation, data science are absolutely key. One of the most obvious ones I think you could use is reliability. You know, anomaly detection. Anomaly detection is probably one of the most common use cases I do across all industries. I've done it with, say, cybersecurity, we've done it with server health, we've done it with detection of breakdown of vehicles, and of course it works for Formula One as well. You know, that can be in real time, just looking for an anomaly. You can do it on sound, you can do it in sensors, heat, voltage, anything that you can sense. You could then look for anomalous behaviors using things like neural networks or simple statistics. And then I'd say the last 2 things that, again, we've had a big impact working with Mercedes on is visual analytics in the car setup and race strategy and simulations in general. So visual analytics, where I did most of my work with the team, and that's like prepping for the race. So a lot of the time when they're going to the circuit, they run loads and loads of simulations, thousands of results, and then they've got thousands of columns of different inputs into that simulation. And somehow they've got to find the right setup out of those like masses of data that's difficult to handle. So they use visual analytics of a very visually interactive way where they can filter and address it and check it, because they need to pick a setup for qualifying, and then it goes into Parc Fermé where they actually have to race their car in that setup. They do that before the race, and then effectively they're trying to preempt the track and what's going to happen on the track. And they'll even be on the plane working with these tools, so they have to work offline. When they hit the track, everything changes. When they put the car on and they see the rubber and the surface, how the surface has changed. They said that even when they were racing the same circuit a week apart, which I think happened during COVID, where they went with the same setup to the same circuit the next week, totally different, didn't work. They would have to reassess everything. And they did that constantly throughout, and sometimes they're taking these things and printing them out to PDF, showing them to Toto, showing them to the drivers. Sometimes having to work offline because the network connectivity at the circuits wasn't good. But they're having to do it all there and then, in the moment as they do their free practice into the race. So these are where analytics and being able to do that quickly is really important. They talk about something called failing fast. You know, if you make a mistake, you want to discover it fast and move on. You don't want to get hung up on it and spend ages researching it. You've got to race the next day, so you haven't got that luxury. Simulations, again, simulations are everywhere. You know, any kind of industry like Formula One, you're going to simulate everything, and that again generates lots of data, and you need a way to delve into that, and you need a way to run simulations. So the demo I'm going to show is sort of touching on that idea of simulating a race and showing how we could improve how somebody races around a lap. But suffice to say, there's just a huge amount of data and analytics in Formula One. It is constant and everywhere. And they have a huge team that sit at the garage all the time. And they've got a race team that sit at the garage actually monitoring the team who are out on the track, because they're limited in how many people they can send to the track. And they're constantly communicating with dashboards up on the screen. One of the big parts that they have, and there's a really good video of this by Anthony Davidson, who is an ex-racer and works with Mercedes. Their own simulator is incredible. It's incredibly complex, incredibly expensive. And this is just, that's some Spotfire dashboards they're using there to analyze it. But they have this race simulator that you can go in and actually race the circuits and then try out things and test things, and again, generate lots of data. And that is absolutely key, again, to their success. So what I'm gonna do today is I'm gonna talk a little bit about how you take all the data from things like the simulator and then actually show you our own TIBCO F1 simulator, which is obviously much simpler than the Mercedes, because it takes up a massive area and costs hundreds of thousands, and then take you through a data science example of how we use that race data. But I talk a lot about visually driven data science and why it's so important, and this is something that I've been doing, all my career, pushing out, and what I mean is by having interactive web tools or apps that can run data science and using code where you need code. Sometimes people think data science is Python. It's not. Data science is building models, it's prepping data, it's going into production. We should use code and things like Python where it's best used and use other technologies where it's best used. Don't try and do everything in one thing if it doesn't suit it. And for instance, I think interactive visuals is best suited outside Python, but Python's great for modeling and data manipulation. So it's really using the right tool for the right job. And what I hope to show and get you to maybe agree already, or at least you'll have a thought about after the demo, it provides a more interactive, intuitive way of doing data science because you're being driven by analysis and actually spending your time on the data science rather than coding. How much time, if any of you have written any code in any language, have you spent debugging or writing the code? There's a lot of time lost, and that's not really doing data science. You want to be analysing the models. If you can build visual ways to call into data science and do analytics, you also remove the barrier of entry for a lot of people. Do we need to be a coder to be a data scientist? I don't think you do. If you understand the physics or you understand your domain, you should always be working with domain experts, then that removes that barrier. Some fears I've heard is if you can't write code, it reduces flexibility. I would actually argue by using code and parameterizing it with a sort of visual front end, driving that, it's actually more flexible. Another thing I've seen a lot of is how sustainable data science is. How many times have you seen, if you're working in that, there's a code base that somebody doesn't know what it does, or it's so old, or the person left, or it's a project they forgot about, or it's 10,000 lines and nobody wants to touch it because they're scared. That happens a lot. So I think, again, if you can reduce code base and use other tools to interact and make things much more clean, you get a much more responsive and reliable, a much more sustainable thing that other people can pick up. And one of the other things is, as data science, especially with ethics around AI and data science and what data you use, especially in things where GDPR or people information is used, you also need to make it explainable and auditable. We need to be able to show what data we've used and how the models are working and what they're doing. And again, if you've got huge code bases, that can become hard. So I love coding. I've coded all my life, but I just think we need to make sure, and it's always worth thinking about when is the right time to use something like Python or R, and when is the right time to use other tools as well. And what I hope to show is that it actually improves the quality of data science you do, because it makes this much more interactive. I spend my time analysing the detail of the models in great depth rather than writing the code. So there's a couple of examples of this. I used to work at the Scottish EPA, and we did that a lot there, and we produced hundreds of analytics tools and models, and that was really successful. And this small snippet here on the right was by Robert F. Smith, who owns Vista, who owned TIBCO. It's a private equity firm, but he talks about technical debt when he's talking about investing. He thinks that was very important, and people often forget about the technical debt a company has if they over-engineer and over-code. So I'm going to move on to our simulator, which, as I said, isn't as grand as the Mercedes one. But what we're doing here is actually quite similar to esports. Esports is kind of taken off in the world, and we're using the official F1 game here. So this is from Big Data London 2019, just before the pandemic. So again, I would wish I had a newer video, but we've never done this in person with the car since, thanks to obviously what happened. But I'll show you the video. So we did this with Mercedes at this event, and what this person doing is he's inside the Mercedes car. This is like a real shell of a Mercedes car, and he's racing this game. You can't hear the sound, unfortunately, but you hear the game. So he's racing it there. And then what we've got here, and I'll show you a demo of this, is actually a live streaming dashboard. We have the feed coming in of the car, so you've got the speed, the steering, gears, etc. You've got G-forces and you've got temperature. I'll just keep that same so you can see, so you can hear it a little bit, and you can see the graphs moving along all in real time. But one of the things to note with this is that up here, you'll see there's a predicted lap time. So it's saying 1.11 seconds, and then it's got a current lap time. So what we're actually doing here is we're running a data science model that's calculating every second or more than that what we think the end lap time will be. And we're doing that by taking all the sensor feeds off that game or the race and actually building a model to do that. And I have to say, if you ever see something like this at the events, go and try and sit in it, because honestly, I don't know how you sit in that for 2 hours, because you're so absolutely crushed in. It's not comfortable at all sitting in that car, but it's great fun. How does I won't spend too long on this, because I don't want to spend too much time, but this is just how we do our technology at TIBCO. You know, we can do a lot of real-time analytics. So we're taking the game. So this is an official Codemasters F1 game that's used for the esports. And you know, all the big teams have esports drivers, and actually using esports drivers now to do simulations for them. It's got so realistic. It's going through some technologies like Flogo and MQTT, which is helping us stream it into our sort of data science and analytics platform. So the real meat of the tool is here, where it's streaming this data in TIBCO Streaming. And what it does is it pushes it out to Spotfire, which is the dashboard you saw, but we also importantly store it in Postgres, and that allows us to do historical analysis and modeling. And then we put data science on top of that, powered by Python or Spark or whatever we want to use, and then we can push, you know, using model ops into a repository. And we can do this all in real time, so we can deploy models live. And I'll actually show you how we deploy models in the demo that I've got. So just before I jump into the demo, this, just to give you a feel for the amount of data that even comes off the game, is really impressive. So one lap of Brazil generates about 100,000 data points. So it sends out a reading from the game every 10 milliseconds or so. So you get a lot of data, and there's about 140 parameters in that. So it's a reasonably big data set, even though it's just coming off a computer game. So let me do my first flip and see what happens. This is a potluck that you take when you do something live. So this is a dashboard, and we're running a simulation of someone racing around this lap just now. And fortunately, as I turn it on, they're at the start of the lap, so the graphs look a little bit wonky. That's why you're seeing these straight lines. But what we've got again is you can see the current lap time here. You've got the predicted lap, so that's running probably on this circuit, a random forest model, to predict the final lap time. We've also got a model running, telling whether the likelihood of crashing is high or not. So when we do the simulator, obviously it's random people who've turned up, it's not F1 drivers, so you get a huge variety of abilities, some wild and wonderful attempts at a lap. And that's what we tried to do, is we thought it'd be quite interesting to try and predict if someone's going to crash or not. So it'll look at things like, how often do they touch their wheels off the circuit, how often do they dip a rear wheel in into the gravel trap, what line are they taking through, have they damaged their wings in any way or form. So this is quite a clean lap, but this is what we're doing, and this is our ultimate aim. So I'm going to take you through how a team analyzes data that comes off a lap like this, which is very similar to what Mercedes do, and I'm going to actually show you building a data science model as well that produced this prediction. Then we're going to do some analysis to actually show how you could then use that to improve and learn how to better your lap and how to improve your race time. So what we've got here, and like I said, this is all powered by a Postgres database, is I can actually go and tell this dashboard what data I want. So I can go to my setup, and I just warn you, if you like line charts, you're going to love this. If you don't like line charts, then don't get into F1, because it's all line charts. They love line charts. I've never seen so many line charts in my life. But here we can come in, you can see all the circuits that we've got data for, and I can click in any circuit and see what race laps we've got. You can see, for instance, the name of the person, what type of lap it was. OSQ is one-shot qualifying. So what we tend to do is we do one-shot qualifying, and we pick laps and we'll analyze that. So this is quite similar to what the teams do. They will have all the laps either from the simulator or from an actual race or pre-season testing. And what you can do is select a few laps. So I'm just going to apply a bookmark which will select some laps I've picked before. And I'm just going to go and show you those in the setup. So now we've picked 3 laps, and we can see the time they were raced, and then we can see the final lap time. So in purple or pink is the fastest lap as always, and you can see it's 1, 3 or 4 seconds behind. So what quite often you'll do is an analysis like this, where you have your 3 laps at the top, and this bar chart's just representing the time. So the shorter the bar, the faster the time. And what we've got importantly here is the delta calculation, where we've calculated and normalized the time as they race around the circuit, because they're in different positions at different times. We needed to use some normalization. And this is, for instance, the distance here, so 0 meters to the 6,000 meters or just less that is Silverstone. And the red line is this red lap, and then it's showing you how fast the other two drivers were versus that. So you can see the blue driver, it was a lot faster. They did a much faster time, whereas the yellow driver was worse. So what you can start to do is analyse this. You've got some of the basic inputs that the driver has, such as brakes, steer and throttle. You've got things like speed and RPM. And we can say, well, let's look at a part of the circuit and see where there's differences in how people do. Because we can analyse this, but it's quite messy. But for instance, so if I take this section here, which is right after the starting straight in Silverstone, it's quite a tricky high-speed section. You can already see a difference. You can see that the blue driver instantly chops off half a second of time. They're much faster than the other two drivers who are quite similar. And if you look at the traces on the left, you can see sort of differences in style. You've got throttle. So the blue driver never drops their throttle. They're full throttle all the way into that curved area. They are able to hold their speed. You can even see as well their steering is quite different. They're much more, their steering's at one angle, so that means 100% one way, and then they're very quickly with a slight adjustment the other way, whereas you'll find slower drivers will kind of gradually turn. So the fastest drivers are very quick to turn. So you start to see even insights there in how they do that, and you can even see the brake temperature shows you that the other drivers are braking early because they think they need to brake for the corner, that chicane, but the blue driver, who's a better driver, knows you don't need to lift. So you can start doing that for all parts of the circuit and start looking at areas, because there are some areas where the red or the blue aren't quite as fast, or there's a mistake made, and you can really delve into that. And you can see how I'm interacting with them, actually marking the circuit map, any area I want. And this is what I mean about visually driven analytics. To do this without a tool like this that allows you to do this, and this is the typical Spotfire tool, is incredibly difficult to produce all these visuals and make it interactive like this. And we can do that for all sorts of parameters because we've got all these different parameters such as pitch and yaw. We've got the wheels and where they were placed, and we've got things like suspension loads. So you can do a lot of in-depth analysis. So that was just some of the analytics, and the teams do it. If you ever watch the TV and they show the graphs, you'll quite often see line charts like this being displayed, and then they'll analyse that in the same way, and they'll look for very minute differences between where a driver lifted, what gear they were in, how much brake they applied, looking at race starts, who pushed too much into the car and burnt rubber in the start, who came off it cleanly, etc. So there's all sorts of stuff that you will do just with the strength of analytics without even needing to touch data science yet. So let's try and do some data science. So what I'm going to show is the data from the game that you just saw streamed. And then I'm actually going to show you building some models, and this is how we integrate with Python, but power it all visually from this tool. So I'll let you see the data quickly. This data here, this is the raw data that comes off the game. So what you can see here is you've got session times, you've got a whole load of parameters such as lap distance, so it's showing you in meters how far they're through their lap. You've got all these parameters such as speed and throttle, positional data, your velocity in each axis, G-force, suspension loads, everything for each wheel. It's a huge data set. So there's about 140 or so parameters there. And what we've done in this tool is we can query the data sets to pull that in. So when we use this front end, we can say, what track do you want? And simply click load data. And this is an example where we've replaced code with a tool doing it for us, because I don't want to write SQL to grab data. That's not what I'm interested in. So when I click load data there, what I'll do is I'll go to my Postgres database and I'll query these three tables, and it'll automatically join them all using SQL-like joins. And I can design this visually. I can even add parameters on it. So I've calculated a new feature here where I've used some simple expressions to look at where the wheel is on the surface and generate new features. But this is nice because I can audit this. It's much clearer to see. So this is just one example where I think, we don't want to be writing lots of SQL code. If we can avoid it, let the tool do it for us. Well, once the data is in, again, we can sort of use this to, again, interactively analyze the data. So one of the key things we've found is if you look at the data set overall, we're getting a reading per, every 10 readings per second. And that's just what's happening in that moment. So that's not really good for data science. What's happening in a millisecond or 10 milliseconds doesn't tell us a lot about what the driver does. It just tells us what they're doing in that moment. For a model to predict what a driver is doing or how well they're driving, you really need some of the history. So the simple way of handling that, because models and the ML models need one row of data to build it, to predict from, what we did was we actually calculated rolling averages from that. So we took that data and we used a Python data function, and I'll show you how we use Python in these tools. And it basically calculated 3-second rolling averages to give some sense of history in the data. Once we've done that, we can actually analyze the data. So this is showing you your 3-second rolling average for speed. And you can see what we do is the fastest drivers are in purple, the slowest in white. And you can see obviously the purple's more at the top, so people who carry more speed through the circuit are better drivers. And you can pick any parameter out of the 140 or so. We can look at gear, we can look at DRS. You know, some of them are useful, some of them are not. And of course, when you're building data science models, you're looking for what parameters are the best features to put into a model, which ones will separate and give you good predictions. But a lot of it's so messy, and you don't want to go through 140 parameters manually. Another thing we've got here is, on this bottom left, is a histogram or bar chart showing the profile of lap time. So 89 seconds is the fastest lap, and 100 seconds is the slowest lap. But what you can see by just doing simple analytics, because I think doing analytics before you dive into data science is really, really important. We can see there's almost clusters of drivers. You know, there's this sort of small section of really fast drivers. There's about 8 laps there. Then you've almost got a sort of middle section where most drivers are sitting. And then you've got a sort of maybe 1 or 2 clusters here of the poorest drivers out there. And that might help us because we could build models per cluster rather than just try to model every type of driver. Or we could try and predict what cluster you're in and then show you how to move out of that cluster into a better cluster. So yeah, I mentioned about going through the analytics and all the parameters, but we don't want to do that. We want to use some data science to actually do that for us. So this is the first instance of Colin's Python from a visual front end. What we've got here is all the parameters, and I can select these, and I can say, well, I want to put these parameters in, and I want to do a feature importance analysis. And what we do for this is we found that if you build a model per sector of the track, it's much higher performing than for the whole lap. So that's why you see 3 sectors. Every Formula One track is split into 3 sectors. So we're going to build models that are unique to each sector rather than building one overall model. And I can just hit determine importance. And what that does now is it actually sends all the data and all my setup and all my hyperparameters, if I'm using them, into Python. Python will do the, using sklearn in this case, will do the feature importance, and then it'll pass the results back to Spotfire. I'm just going to kill that for the sake of time, because it takes a few minutes to run. But what you'll end up with is all this importance, and you can see the different parameters of the game, and you can see which are marked most important. So XV, that is velocity on the x-axis. ERS deployed is energy reduction system, you know, how much energy they've deployed, and throttle and things like that. But you do see it's slightly different per sector, highlighting that. Another thing I want to highlight just before moving on is a thing that I see often is when you're splitting data into train and test, people will sometimes do it in the code or just do it randomly in the code and hope it's right or not check it's right. So what I'm doing here is I'm actually splitting the laps rather than splitting the data because I need to keep a lap as a whole. That's the first thing. You don't want to chunk a lap into different parts because then you're not getting the full story of the lap. But also I want to make sure, because I've not got a lot of laps, I've only got 80, so we're not building a lot of on a lot of data. I want to make sure my test set really represents the profile of my training data. So I can like randomly pick different data and I can see different profiles. So if you just change the random seed, you can see it's giving me a different profile. So effectively, I want to visualize the train and test split to make sure I've got a realistic and fair distribution. Because if you don't, you'll have a model that's biased when you test it against that test set because it's maybe you've got too many fast laps or too many slow laps. We can also do things like play about with the coding, and that'll all get passed into Python and it'll do text encoding. This case, we've got only numeric data, so that doesn't apply. So I'm going to spend the rest of the time on the actual model and the model results, but I just want to show you this first just because I quite like the visualization, to be honest. But another thing you can do is correlation analysis. So I can pick a method, and again, this is using sklearn, and I'll say, well, let's flip this to Kendall, and I can click calculate correlation. So it's now taken all the parameters I selected here, that are in yellow, and it's doing a correlation analysis of all those, and then I'm using a network chart to analyze it. So for instance, I can now look at hotspots. If I say, show me things that are 70% or 0.7 or higher correlated, you can see the sort of different parameters. And you might want to then exclude these from your model because it might be too biased. And you can sort of see patterns as well, where you get these sort of nice chains of correlation all stuck together. And it helps you understand as well how the data is correlated. And of course, because it's coming off the car, it will be heavily correlated. So I tend to not remove things in this instance. But it's just a very nice visual way, again, of sort of examining correlation, seeing outliers, and seeing where possible issues might occur. So building the model is the most important bit. What we do here is we build 3 ML models, random forest boosted trees and regression, linear regression or elastic regression. And we build a model per sector. And if I click build models, it will start kicking off 3 model types per sector. And it will push all the data into Python and then return results. So I've got these results, and if I want to change, so for instance, my feature selection, I can just come in here and I can go back and you'll see actually there's only 25 features now selected, or if I want to build it with all of them, I can just go back. So it becomes very interactive and I can keep clicking build and get new metrics to see what's best. But what happens once you've done this, so if I click build, it'll trick off and I won't let this run again because it takes a while. You'll see it builds a whole load of models in parallel. Again, it's calling out to Python with the code just needed for those models. Then you get back metrics. So I'm using RMSE to see, what's the lowest lap time, the lowest residual of the lap predictions. So random forest comes out as 1.3, so 1.3 seconds within the actual lap time. We get R squared from the random forest of 0.995. The rest are also very high. And then we can see the best RMSE per sector. Because what we're going to do here is when we deploy this, we're going to send out the individual model that's best per sector. So again, you don't need to use one model. You can use a multitude of models. You can use specialist models when you're doing data science. You want to optimize that and not just be fixed in one model that does all. But there are pitfalls to that. And one of the things I always say is always put your models and data into domain context. I can analyze this. And again, this is part of the visual element. I can look at how does the model do for slower lap times? How does it do for faster lap times? How does it do in the final sector? And you can see there's some really wacky results here. Or how does it in sector 2? So I can look at subspaces of data and analyze the residuals and the plots and the hotspots of bad predictions where the models predicted the lap time wrong. But to do that effectively, and I think this is true of all data science, you want to put it into the context of what your domain is. And so what I want to do is put it in the context of a race driver going through laps. So what we have here is every line chart is one individual lap. And then the lines here are the predictions or the residuals of each model. So we've got the boosted trees in blue, for example, and then the random forest in yellow. And the green line is 0, so it means it's a perfect prediction of the final lap time. So you can see quite clearly that at the start, the models all they all sort of predict a slower lap time, 5 or 6 seconds off, which isn't great. And then as they get into the other sectors, they get closer and closer. But as I look down all through the laps, starting with the fastest laps, you can see they start too high. If you go to the bottom laps, so they all start too low. And in the middle laps, they're about right. So it's already telling me something that my metrics and R squared and plots of residual didn't tell me, that the models are tuned to the middle. And that's maybe because our data is biased in the middle. So I've already learned something. But what I can also see as well, the metrics told me that sector 2, the elastic regression, is the best model. But if I actually examine those models, so if I just filter this to 3 example laps, the red regression line, you can see it's quite a funny shape in sector 2 where it's apparently better than the random forest. The random forest is always slightly above, so always adding too much time on, but it's much more consistent. So when I want to see this in live time in that dashboard, I actually prefer the random forest because it's not going to jump around in predictions. Whereas if I use the elastic regression, even though it's slightly statistically better, my predictions are going to go up and down a lot, which will look quite strange. So I want, for production, a consistent sort of answer. So to handle that, when we deploy a model using like MLOps or something, we have a final page where you can actually override. By default, when we automate this, it pushes out the best model from RMSE, but I can come in and override that and say, I want to use random forest for sector model. And now when I go to my optimal model, which will be shown in purple, it's now using the random forest line here. So once we've got our optimal model, we want to actually understand what the model's doing. That's where model explainability comes in. So we're going to use SHAP analysis, and I'll run this live. So if I select this area here for these 3 laps at the end of sector 2, you can see the fast lap, medium lap, and slow lap. What it's actually going to do is, except it's crashed. See, I knew this would happen. This is the perils of doing things live. Let me just reselect all that. So if I'm going to highlight this, and hopefully it will work this time. Nope. Oh, I know why. Apologies. Let me just unselect that. If it goes wrong again, I'm just going to put Poppy on the screen and leave it. Okay, now it's working. So if you've done model explainability, the two most famous methods are LIME and SHAP. I do like SHAP more than LIME because I think it's easier to understand. So what it's done now is it's looked at this section of track, and you can see the colours and the trace of how the drivers did that section. You can see that blue was the fastest lap and takes a different line, red a slightly different line, and yellow again. And what is said is for this section of area, the models are telling us that ERS deployed, the rotation on the x-axis and wheel speed and gear are the most important factors for predicting lap time. So therefore, we can use that to say, if you want to improve your lap, you need to influence those ways or think about how that builds up. So we want to drill into that. So you can see, for instance, here, what's happening is it's saying the more to the right, the more seconds it takes off your prediction. The more to the left, the more seconds it adds to your prediction, so slower lap. And we can drill in and look at the profiles. So for instance, if we want to look at ERS deployed, we can see the ERS deployed trace here. So I can start to analyze the difference in these key components that this model has told me is the most important parts. For instance, wheel speed on the rear right, for some reason for the blue, which is actually the fastest lap in the end, is very different, and it says that's not an optimal way to race that section. We could look at something where tyre wear is higher for blue, or we could look at gear as an interesting one. So here we see the blue car, which does do the fastest lap overall, but not necessarily in this part, holds a higher gear for longer and goes into a higher gear than the other ones. So you can really delve into this and do some really detailed analysis. So what we've got here is the model prediction here in terms of time left in lap versus the distance. So you can see the blue line's predicted to be very fast and the red is slow. And we can highlight this area and say, well, why is blue faster at that point? And we can see they maintain quite a good speed. Their gear is high again, consistent. Their throttle was much more consistent as well. But we notice that red sort of comes in and matches blue at the end. So again, we could look at this area and say, well, why is blue and red suddenly matching, whereas yellow's lagging behind? And then you can see things like speed, differentiation, and look at different parts of the track. So this sort of analysis, I get lost in this because you get so many different stories and there's so many things that are local to that corner. You know, you could do a very fast lap, but take this corner really poorly. So this model might help show that this actually, you know, this wheel speed in the rear right was wrong for the fastest driver. So I can do that again with any other sector. So if I now go to this corner, which is like one of the final corners before the finish straight, and you can see again that there's quite a difference in the line. Blues really hugged the apex, whereas yellows came out and actually gone off circuit quite a lot, and red's in the middle. And again, SHAP will try and tell us what was the most important things to do that fast. Why does it think and predict blues a faster lap? So SHAP takes a few seconds to run. But this is really sort of what I'm talking about, the amount of analysis that we do. And this is still a work in progress, you know, to try and bring this up and understand these laps and check the models becomes huge. And finally, you do then want to push this into production. And what we do is automate this end stage where we deploy models as PMML files. One thing I've noticed is that you'll notice in my building the models, I didn't have any hyperparameters. And that's because we fixed the hyperparameters because we have a limitation in production and size of PMML files. We have network potential issues when we're on different places. So we took compromises. So one of the things that when you're going to approach data science to think about is always you might not have data available. There might be compromises you have to make. So you might not be working with the best or most optimal setup. So that's came up there, and now we've got a different analysis where, you know, it's shown that, again, on the Z-axis, blue is the fastest. In the XV axis, blue again is doing the better lap, and you can see here clearly the trace of velocity, and the X-axis is much better. So you can spend all day doing these, but this is the idea of simulating and learning how to drive using a model. It is a work in progress, and I actually built this week using an LSTM model, so a neural network. And LSTMs are great because they can handle time series, and I think that would be better. But when I ran this, I came out with crazy good answers, and I don't know, maybe it's my personal eye, but I think, oh no, something must have gone wrong. It cannot be that good. I've somehow included the target or I've messed it up, but I'm going to delve into that hopefully after this and see if it's real or not. But it's always good to explore different models and look at their pluses or minuses. So I'll finish up and just say there was an and beyond that we do. Data analytics in sports is absolutely everywhere. I have got demos of these, but we don't have a lot of time. But we work with the professional women's cycling team, where we've built dashboards analysing their heart rates, analysing their power outputs, and tracing that and showing their strategy on the maps. Cycling's got so much strategy, it's incredible when you see their position on the circuits, or the routes rather, and how they change and their different power profiles. We've even done things with NBA and other sports where we use principal component analysis and similarity metrics to look at scouting of players, putting in all the metrics, saying who matches the most using PCA to reduce the dimensions and then do a similarity. So there's so many great things that you can do with this sort of visual way of pulling in data science, etc. I think I will stop there. So thank you very much for listening. I hope it was interesting.
That was great, Colin. Thanks very much. Yeah, we'll get the Q&A started quickly. Do we have any questions in the audience? Yeah, sorry, Kat. Just get this chap up here.
Hi, thanks for a great presentation. So I've done some work myself in cycling, and one of the issues is, and sport in general, and one of the issues is quality of data. Do you have issues with that? And if so, how do you get around that?
Certainly in the cycling data I've seen loads of gaps, loads of mismatches, traces from their spikes, from their devices not matching, so having to put in things like adjusting times and distance, so they actually, so what I've done is actually plotted the profile, say altitude being recorded, and I could see where there was a shift and try to shift the data back. That game's great because the data's perfect, so it's like a data science dream, it's never wrong because it's a game, and there's no issues, but yeah, it's a huge problem. Particularly Mercedes and other teams like that, the amount of data that comes in, a lot of it comes in files in proprietary formats, and then they've got to match it up with other systems and data. So it is a massive problem. The old saying is that you spend 80% of your time trying to fix the data, and it definitely is true. I think the most important thing is to understand the limitations of what you're doing. It's very tempting to just try and build models off it, just because that's the fun or glamorous part, but you've got to be honest about the limitations. If you can fix it, great. Maybe you fill in nulls, maybe use some linear regression to try and fill gaps with sensible values or whatever. But if something just isn't usable, be honest and don't use it, I think.
I think we've got a question at the back.
Yeah, I just wanted to ask, how much do you factor in the balance of probability with regards to rain and weather? And we know a couple of years ago there was a driver killed because a crane came out to pick up another car.
Yeah, absolutely.
And that wasn't even thought about in contingency plans. So you forecast a lot of things, but there's still things that catch you guys out. There's still things that catch out NASA with data.
Absolutely. I think that's really, see that very first quote by Mike Sansoni, I think he's done some YouTube stuff. He talked about that point one of uncertainty, and that's what they're trying to preempt, but they simply have too much data. So all you can do is run as many simulations as you can, try and look at all those things, constantly learn from, like, when that accident happened, I think it was Gilles Bianchi and Adrian Suttle came in, and because the crane was still there, like really tragic. The sport learned from that. Halo came in, things like that, and they've saved the lives, as you saw with Grosjean last year. So you cannot predict them. The weather and the track change hourly, and they go out on it, and the rubber's totally different. They don't even have the data for that. So it is a constant battle of catching up on that data and running simulations to anticipate it. And they have years and seasons to look at that. But because the cars change, how applicable is the previous season? So they're almost starting afresh. So it is a huge, huge challenge. But I think you've just got to like they say, they try and fail fast. If they make a mistake, learn from it and move on quickly, and find that mistake quickly. You don't let it linger. So.
Yeah, it was a really good presentation.
Thank you.
I work in the financial industry, and we pick up a lot of tools and drop them quite quickly as well. One of which has been Spotfire in the past.
Yeah.
I was just wondering what your reasons of choice were as a DV tool, a Spotfire, among some of the competitors like Power BI. And also, I know AWS are coming up on their DV tools as well. On the subject cloud, we saw obviously you having compute issues whenever you were running some of your dashboards. With something like F1, how are you able to kind of increase your demand for compute with real-time sensors coming in at a rate of knots?
Yeah. So there's a few questions in there.
Yeah, sorry.
So Spotfire, that's TIBCO's tool. That's how it works. I actually used Spotfire for 8 years before I went to TIBCO. That's how I ended up at TIBCO, at the Scottish EPA. So I'd used it, and what its strengths were, because Mercedes have other tools like Power BI, and lots of business do. One thing I would say is almost all businesses, a lot of them say we want one tool to do analytics and dashboard. It never, ever works. I've never seen a company do it successfully, because these tools have strengths. Power BI is good at certain dashboard and things, Tableau's good at certain things. Spotfire's strength is good, amazing mapping and geoanalytics, and the Python integration that's sort of leading the field. So you find, like in Mercedes, they replaced loads of stuff with Spotfire because they had all these things written in C, written in MATLAB, and Spotfire could integrate with them, call them, and it also could bring the data together in ways that other tools couldn't. So they found that niche. It's a very good technical tool. So I think it's, like I said at the start, it's about using the right tools at the right time, and finding that for you. So, excuse me. For cloud computing stuff, as far as I'm aware, the teams don't use cloud compute. Connectivity is a big issue at circuits, depending where you are. So they often rely on tech there on site or communicating back with the garage. So for instance, the car setup work I did, working with the team with Mike and others, they actually, one of the things they had to do is they had to be able to do it offline. So they had to load all the data into memory on a laptop. And sometimes they just printed it out in paper, the results in a report, and because they would hand that to the total or the drivers at a meeting. So they often had issues like that, and when they're on the plane. But when they're in the base, I think most teams do most stuff on-prem still rather than cloud, I believe. So I think so anyway.
Surprising.
Yeah, I think they are transitioning. I can't say for definite. I mean, I don't know for about other teams, but I think at the moment it's because they had so much infrastructure and they've got so much power there. And again, it's maybe they have issues with connectivity or whatever, or security. So.
Perfect. Cheers. Any other questions? There you go.
Yeah, great presentation. Really interesting to see how you're using TIBCO. I used to use it a lot actually a few years ago, so it's interesting to see how it's moved on in the time since I've not been using it. Mm-hmm. So my interest is in, there's a lot of like great information that you're presenting from, all the models you're running, all the data you're crunching.
Yeah.
But my impression, having seen it, is in some cases there's probably still a lot of like, so what kind of analysis, like there's still like a gap in terms of how the consumer of that information has to understand what it means and therefore what action should take. And I was wondering whether or not it's kind of on your roadmap to kind of close that gap a bit, to make it more prescriptive in terms of how you can like give them suggestions in terms of what they should do, not just predicting what could happen.
Yeah, absolutely. One of the fundamental things, and I probably should have said this, but when you're standing up here, you forget half your things. You've always got to keep an eye, a very strong key purpose. What are you trying to achieve and what action will be taken? Like you say, that I'm very against dashboarding for the sake of dashboarding. There's a lot of that goes on because it was trendy, it looks nice. You want to take an action from it. If you cannot take or learn or do something useful, then why would you spend your time in it? And it's interesting, so that sharp analysis stuff, that's where we're trying to get to the point that we could use it to say to someone, you took this line, the models say you should take that line, so try taking that line next time. So actually to give actionable insights. But there's so many dimensions to that model explainability in terms of, because it's across a whole part of the circuit, where you are in the circuit, plus the way the SHAP works, it looks at you compared to other drivers and other models. It's quite complicated. So we're definitely doing that and trying to move towards that. But we've do other examples, like we've built recommender systems. We've just been playing a demo like to help people, to help tell them how to reduce energy costs, for instance, by looking at their usage patterns versus in clustering. The PCA one with the basketball, again, the idea there was you've got all these players, college players. Sometimes it's just good enough to hotspot. Here's the top 10 we think you're worth looking at. It's like the wind tunnel example. Trying to hotspot or just rank, here's the top 10 to look at that our model thinks are better, and we think you've got a higher probability of success. So yeah, I totally agree. Everything should have an absolute purpose. and an action you should take from it.
I think we've got time for a couple more.
So I think you mentioned earlier that you've got lots of data, maybe too much to use, which is a nice place to be, I suppose. But one of the things that a lot of these companies do things like Formula One for is because they can get advertising, but also they can invest a lot of money into materials research and they get something out of it. Like Mercedes takes away technology and sticks it in their commercial cars. So you've got a huge amount of material science information, you've got a huge amount of mechanical information about the cars that you can add and kind of embellish your data set with. Was there ever any attempt to look at that? Maybe like brake materials, which ones work best when you're braking, that kind of thing.
Yeah, I've never worked with the team, and the work I've done has always been more in car setup and simulation. But they have 2 factories, and one is actually, and they have a company that builds engines as well. I think it's HPP. So they have a factory that does the parts just down the road from their factory in Brackley. So that is something I absolutely guarantee they will be doing. During COVID, they looked at building ventilators and things using the tech and ideas, and that was something they tried to do. The 3D printing stuff, the technology they have is immense. So I've no doubt, because these are businesses at the end of the day, they want to commercialise what they do. The teams want to advertise, and they've all done partnerships and work with lots of companies to do that. So yeah, I would be amazed if they weren't doing that.
Perfect. Yeah. Sorry.
Thanks. Yeah, I really enjoyed that presentation, and specifically how accessible you made the information. I think a lot of us can imagine Toto Wolff into the wee hours going through every single corner and looking at the data. I think that's brought it to life. I think there's so many different questions I could ask you about that, but I'm going to go in a different direction if this is one of the last questions, and maybe ask for some trade secrets. If you're talking about the fact that it's kind of flat files and on-site track data, is there any sort of data swapping between the teams? Do they sort of try and bring together some data that's not going to give an advantage away, but will help each other out probably for safety concerns, the gentleman behind me said?
Yeah. I'm not sure if they share any data or not. I know there is software that they all use, for instance. There is software that they all share and use that are produced by certain other teams. So there is some sharing of technology, but I don't know if they ever share their data. I've done work with football teams, and for instance, they can all tap into the data of other teams. It's sort of given by the governing body. So I would imagine that the FIA have some data that they must share for safety reasons and other things for that purpose. But I don't know if they're very open in sharing with other teams. I don't know if they share with, how they've got some connected teams through their youth teams and things like that. So yeah, exactly. I genuinely don't know how much goes on. Yeah, so sorry to give you almost nothing answer.
Yeah, sorry, we got another question at the back.
Mercedes are doing quite a lot with the America's Cup teams. Are you starting to get involved in the America's Cup and sailing and stuff like that?
Yes. Yeah. Because they're all under NEOS and things like that, they often again see the technology that Mercedes do and they want to try it out. So yeah, we have started to speak to the America's sailing, the American Cup teams and things like that. So that's definitely something. I mean, we're in a lot of motorsports, not just Mercedes as well. So we do work with other teams in other sort of genres of motorsport as well, who do very similar things to what I showed at the start with the analytics rather than the data science. That seems to be one of the key areas they all want to do.
Last question. Just here, Kat. Just yeah. Sorry. Oh, the chat behind. Oh, you got to let both of you go. We'll get a couple of minutes on you go. It's fine.
A brilliant presentation, thank you. I was kind of more interested in, as you mentioned at the end there, the other sectors of sport that are obviously have been embracing and continue to embrace at a very advanced level data analytics. And that, within the F1 scenario that you gave there, it's incredibly advanced, incredibly in-depth, but, is there a ceiling that it can hit, or have you got any insights into where it goes next in terms of how does it evolve? How do you get better at it across not just F1, but sport in general?
Yeah, that's a tough question. Good one to put it then. Yeah, I think, F1 and the sports I've seen, especially F1, so advanced and so much data, but they tackle the same problems that everybody does, like just accessing the data. You know, that is the sheer volume that's coming off the car. That is a huge problem. I don't think they've got to grips or full potential yet. There's a lot of sports, I think, that are rooted in physics and mechanics that they're still using that sort of viewpoint to it, and maybe aren't tapping data science enough at all. So I still think it's quite an emerging trend in sports. Football teams, you know, there's been like Liverpool have put out stories about how much they use in Man City, where you can like heat maps and predict the probability of losing goals. Or remember in Liverpool they showed like a shape of players they found were more probable to sort of score a goal. And I've seen things like that as well, where you can use like image detection of videos of games, looking at where the players go and when it happens, match that to data. So I think there's huge potential, and I still don't think it's peaked yet. I don't know if it's probably limited by the data and availability of people. I'd say the thing I see in the industry, to be honest, the biggest thing is unavailability of data scientists. There's not many, or there's not enough experienced data scientists or data scientists out there, I think, maybe to fill a lot of these companies' ambitions. That would be me, I think, more the limiting factor is actually people availability. So it's a good field to get into.
Thank you very much. I think that's all we've got time for, but thanks again, Colin, that was great, and hope to see you all again soon. Cheers.